So we discussed whales as nature-based solutions, potential for them to be nature-based solutions in terms of their ability to sequester carbon. The discussion is being taken a little forwards, saying maybe they can be, whale conservation can be used as a carbon offset, which means somebody emits some carbon or greenhouse gases and then they pay for whale conservation, and then whales do additional carbon sequestration. The key word there is additional carbon sequestration. If there is co-benefit of conserving whales and increasing their numbers, obviously that's a good thing, but nonetheless economic calculations have to be done. This paper does that, produces an economic model which we'll look at, but their conclusions are a little bit more sobering. So let's start with that. As climate change accelerates, there is increasing interest in the ability of whales to trap carbon, i.e. the whale carbon, yet it is currently undetermined if and how whale carbon should be used in climate change mitigation strategies. Maybe they'll be part of the portfolio, but you have to be sure of the numbers of additional carbon sequestration. Restoring whale populations will enhance carbon storage in whale biomass and sequestration in the deep sea via whale fall. So if the whale dies and falls, it's going to take tens of tons of carbon with it, though the global impact of this will be relatively small. Okay. On the other hand, whale stimulated primary productivity via nutrient provisioning may sequester substantially more carbon, though there is uncertainty regarding the carbon fate in these food webs, in the sense that the carbon that's being exported as whale feces may just get remineralized and recycled and not really take the carbon out of the system. Recovery of whale populations via reduction of anthropogenic impacts can aid in carbon dioxide removal, but its inclusion in climate policy needs to be grounded in the best available science and considered in tandem with other strategies known to directly reduce greenhouse gas emissions. This is like forests. We've discussed forests elsewhere. Forests obviously are very valuable in many ways, and they do sequester carbon as they're growing. The question of what happens if there is a fire and other perturbations, and whether they sequester carbon after the forest has matured and so on, are all issues. Here, looking at the various processes by which whale can in fact help the biological pump in terms of sequestering carbon, is that you can look at the two loops here. So carbon is fixed in these processes from the atmospheric carbon pool. That's of course part of the solubility pump and can be part of the biological pump as well. So let's say we have here the vertical movement of a whale, which is going to respire some carbon, but it's going to produce, it's going to store a lot of carbon, but it's going to produce feces which are loaded with iron, nitrogen, and phosphorus from all the diet it takes in and digests. And that can then provide nutrients for phytoplankton bloom, which can be much larger than the whale biomass in terms of the area covered and concentration per meter cube of the volume, for example, in the ocean. And that is fed on by the zooplankton, which then can do carbon export. Phytoplankton themselves do carbon export as well, even though the amount of primary production that reaches the bottom of the ocean is often 1% or less of what is produced in the euphoric zone. So we are here looking at the mixed layer, which is the well-mixed surface layer because of the turbulence of wind forcing and so on. And in general, you want things to escape out of that region, in fact below the region where there are mesopelagic prey, for example, which are also being which are also fixing some carbon and exporting some of it. So the whale is feeding on them and it's sequestering carbon if it falls, but on the other hand, it's also involved in storing carbon, producing nutrients, as we said, and creating phytoplankton bloom. And the prey that it eats also can be involved. So this typical two types of whales shown here, of course. This is the hypothetical Southern Ocean demonstrated by two end members, so deep diving sperm whale and the shallow diving mysticete. That's the name of the whale. So you can see that they share the same direct carbon pathways in terms of biomass carbon of the whale falls, but differ in their direct carbon pathways, differ in their carbon export and carbon sequestration. So mysticetes feeding within the mixed layer release regenerated nutrients at the surface, stimulating recycled primary production and carbon export. Arrow thickness here indicates relative magnitude of the carbon flux. So this is doing some recycled production within the mixed layer and exporting carbon, whereas this deep diving sperm whale is picking up stuff even from the deeper mesopelagic regions. So you have epipelagic, mesopelagic, bathypelagic, abyssopelagic, and so on, which you can look up elsewhere. Okay. The other part of the story is that there are feeding grounds. This is the North Pacific here, going from Japan through Alaska to the northern North America. Feces with nitrogen, iron, and phosphorus regenerated nutrients. So you can see that's going to drive phytoplankton bloom, which is going to export carbon, but also produce prey biomass, which is going to be fed on by the whale. And you can see the same thing here. Now looking at whale excreta, we looked at two types of whales, but here we are looking again at new nutrients coming from the excreta as opposed to the mysticete, which is doing regenerated nutrients within the upper layer. This produces phytoplankton, so they can export carbon and carbon sequestered, and there are consumers as well. So just kind of schematics. So here it is breeding grounds, migration to nutrient poor breeding grounds. So whales are not only doing vertical exports, they are taking nutrients from rich phytoplankton bloom areas where you have spring blooms that are very heavy in these mid latitudes, and moving them to the breeding grounds, which are typically subtropical waters, so tropical, subtropical waters, where you can have much less much smaller phytoplankton blooms because of the converging circulation not supplying the nutrients, etc., which you can look up in the other podcasts under carbon cycle. So they can then return to nutrient-rich feeding grounds. So there are many details involved, like some of the whales cross the equator, go into the Southern Ocean to feed on krill when they are nursing their young ones, because the krill have much more nutritious nutrition content as opposed to eating at an upper level. So here is this horizontal export of nutrients as well, based on the feeding grounds and the breeding grounds, as opposed to the vertical export we talked about here. So estimated carbon fate: fixed, stored, exported, and sequestered in pre-industrial whaling and modern day great whale populations. The mechanisms include biomass, whale falls, whale pump, which is the migration up and down of different types of species of whales, and the great whale conveyor belt, which is kind of the cycle we are talking about here, and the vertical cycle. I won't go into the details, but the 8 baleen whale taxa occur all over the place, all baleen whales. So this is the pre-whaling estimate, pre-whaling carbon estimate, and modern carbon estimate in okay, I don't know why I got stopped there. So you can see the numbers for various species: blue whales in the Southern Ocean, blue fin, humpback, and Antarctic minke whales in the Southern Ocean, and you have sperm whales. So we talked about Physeter and Macrocephalus, and the blue whales in the Southern Hemisphere. So that's the great conveyor belt where they go all the way back and forth. So this is global Southern Ocean, and Southern Hemisphere. So you can see gigatons of carbon numbers. Generally what can you do? You can compare. Here it was pre-whaling carbon estimate 1.1 times 10 to the minus 2 gigaton, whereas this is 10 to the minus 3. So there is a drop. This is from 2016. And similarly, 10 to the minus 4 to 10 to the minus 5, 10 to the minus 1 to 10 to the minus 3 for blue whales, and so on and so forth. So obviously there is an argument to be made that if you recover the populations to pre-whaling levels, then you have the opportunity to increase the amount of carbon that's exported. Carbon fate, stored, sequestered, fixed, exported, and so on. So these are the various references from where these are taken. So fixed is when they are taking it into their body. So then whale pump is where that's involved. When you have whale falls, then it is sequestered because it is taken out of the system, and when it's in the biomass, it's stored. Okay, so this is exported because you have deep diving sperm whale that we looked at that produces different types of exports than recycling. And so on. So just looking at monetizing whale carbon, whales provide numerous ecosystem services such as tourism in the form of whale watching, enhanced primary productivity, and carbon sequestration, along with cultural benefits such as education, aesthetics, and existence value. Recent attempts to monetize whales have garnered attention by valuing an average whale at $2 million for carbon capture and other services. As authors of several foundational papers cited in these reports, we feel the scientific support for this valuation is lacking. So numbers are basically made up. Here we present 5 concerns regarding the monetary valuation of carbon dioxide removal by whales as proposed by Chamy et al., which is a paper that's being addressed here as kind of a criticism. Whales are proposed to increase primary productivity globally by 1% with no supporting empirical data, so just an assumption. Whales can increase primary productivity, but the magnitude of this varies by species, location, and season, clearly. Whales are absent from vast areas with no indication that they could increase phytoplankton productivity by 1%. That's a massive number if it's converted to carbon sequestration. Organisms' lifespan influences the duration of carbon storage, whereas whales can store carbon for decades or longer. Phytoplankton and zooplankton typically store carbon for days to months. Such short-term storage is generally not considered applicable for carbon mitigation schemes which seek storage for greater than 100 years. Carbon must be transported into the deep ocean or buried in sediments to achieve centennial sequestration timescales for greater than 100 years. One method used to calculate export efficiency assumes that 10% of net primary productivity is exported and 10% of that is sequestered below 1,000 meters, but export and sequestration efficiencies vary considerably by location. So in the high upwelling regions you may have 10%, but most other regions it's 1% or less, as I mentioned before. Regional variation in carbon storage time and efficiency could reasonably reduce the estimated carbon dioxide removal resulting from whale assimilation of phytoplankton production by 100-fold. Thirdly, baleen whales often feed and defecate in the mixed layer, yielding primary production from nutrient regeneration. Although surface feeding whales can play an important role in nutrient cycling, they should have little effect on new production, which is required for using nutrients brought up from below and hence carbon export or CDR. This further reduces the value proposed in terms of offsets. The model relies on overly simplistic assumptions about whale population growth. Age and size structure should be considered due to influences on carbon storage duration. The most advanced work on whales and carbon sequestration was not included in the study of Chamy et al. Whales contribute to vital ecological function and ecosystem services, including CDR and whale falls, yet recent valuations go beyond our current understanding of their role in carbon cycle. To be viable for CDR strategies, carbon removal by whales should be measurable and long-term, similar to the verified carbon standard on land. Field experiments and models, for example Earth system models, could provide the requisite data, but recently proposed monetary values should not be implemented in CDR or other policy strategies. before such scientific documentation. Finally, they do provide an economic model. I won't go into the details. There are many assumptions involved, but you can briefly see that they consider multiple scenarios. Here are the number of whales. This is a stylized representation of the proposed bioeconomic framework. Business as usual is where we don't do anything. Pole 1 and Pole 2 represent recovery paths that are slower and faster at recovering the population respectively. And 3 population trajectories are shown here. Whale carbon associated with each trajectory is shown here. So faster recovery, more carbon faster. This is the business as usual. Somehow they seem they reach the same number of whales and same carbon with the assumptions in this model, so you have to figure that out. But the discount value, where you look at how the money you put in to offset the carbon now is going to be devalued over time. You have to look up other podcasts of mine on understanding discount rate. Basically, $1 you invest today will be worth will be depreciating at some rate into the future, and higher the discount rate, the faster the value will depreciate. It has a lot of consequences. So discounted value is obviously peaks quickly for the faster population recoveries and declines, whereas the other two decline fairly rapidly. And similarly, this is a value relative to business as usual. And here they show the net present value of each policy, which you can look up to see the details. They provide the math and the construction of the model and the assumptions and so on. But the point is that such economic evaluations may be necessary before they can be used as offsetting tools or as part of the carbon mitigation, climate mitigation activities. Okay, so together with the other podcast, that adds some more information, so I decided to include it here. But please be sure to read the Chamy et al. Paper where this is proposed, and this paper where that approach is criticized. Okay, then you make up your own mind.